All right. We are going to talk about Taylor series in this video. It's something we've been looking forward to, maybe. I have been. Maybe you have been too. We've been talking about kind of a mismatch of things, right? We talked about Taylor polynomials to start, polynomial approximation, and then after that we were talking about general power series and learning some properties and tricks with those. And now we're going to push all of that together and talk about this idea about a Taylor series. It's going to be very similar to a lot of the stuff that we've talked about. It's just going to try and tie up a bunch of these topics all together into one package, which is pretty cool. So we'll extend the idea of Taylor polynomials to Taylor series. We're going to find some Taylor series. We'll do some examples. And we want to also talk about convergence along the way. So here's the general idea of a Taylor series. This should look familiar, though, because a Taylor polynomial was the same thing, except the series was from k equals 0 up to n. But we had this same coefficient structure where it was the kth derivative evaluated at the center a divided by k factorial times x minus the center raised to the kth power. And we said this was an nth degree polynomial because we stopped with an exponent of n. But now we're going to let n go off to infinity and get an infinite power series out of this thing. That's it. Exact same coefficient structure, so all of this should look familiar. Quick note, sometimes we'll call the Taylor series centered at 0 a Maclaurin series. I'll probably just call it a Taylor series centered at 0. But if you see the term Maclaurin series tossed around, it's just talking about specifically centering this Taylor series at 0. So all of your derivatives are evaluated at 0, and then instead of an x minus a raised to an exponent, you just have x raised to those exponents. Cool. Here's an example. Let's throw you into the deep end. Go ahead, find the Taylor series centered at 0 for this function sine of x. I'll help you get started on this, but if you want to give this a try on your own, go ahead, pause the video, see if you can figure out what's going on here, and then in a minute, I'll go ahead and kind of walk you through it step by step slowly. All right, let's do this. This is how I normally organize things. First, find a bunch of derivatives. We know we're going to need those. So grab a whole bunch. Notice that we do start with the k equals 0 term. So the 0th derivative is really like the function itself. And then k equals 1 gives us the first derivative, k equals 2, k equals 3. I've pretty much just done those because once I look at k equals 4, the 4th derivative of this function is back to the sine function itself. So that's a nice structure for these trig functions. We really only have to know a couple of these because they're going to start repeating after a while. That's helpful. So from there, what we want to do is evaluate these at our center 0, which is going to be easy because we know that sine of 0 is equal to 0, and we know that cosine of 0 is equal to 1, right? That's just thinking about our unit circle. I recently discovered, there we go, my little circle tool. It gives me really nice circles, unless I draw them poorly. That's a bad set of axes, but oh well. So we're looking at right here, right? This is the point, 1, 0. So cosine of 0 is 1, sine of 0 is 0. So you can toss all those in, make sure you divide out by factorials, and we can get this nice structure. And this is what it looks like. So sine of 0 is 0, right? And so we have 0 over 0 factorial, 1 over 1 factorial, negative 0 over 2 factorial, negative 1 over 3 factorial, etc., etc., etc. Once we start tacking on this x raised to the exponent, we have 0 times 1, 1 times x, 0 times x squared, negative 1 over 3 factorial times x cubed. And then we'll notice that all of the even powers, all of these even terms, these even derivatives are going to have signs in them. And so all of those terms are going to have coefficients that are 0. So we won't worry about those. And the odd terms, the 3rd, the 5th, the 7th, etc., 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 are going to bounce back and forth between positive and negative cosine as you find more and more derivatives. So hopefully you can see these are the next few terms. This sine function, if we write out the Taylor series for it, it's 0 plus x plus 0, so I'm going to leave out the zeros from here on out, minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and then it goes back and forth, plus, minus, 9, 11, 13, etc., 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 forever and ever and ever. Okay, so if you haven't done it yet, pause the video and write the general series notation for this. Write out the general kth term and then use a series with that series notation to have this index set up with k goes from 0 to infinity. And that's the Taylor series for the sine function. Pause the video, give that a shot, and in 10 seconds or so, I'll flip this to the next slide so we can see what it is. All right, let's take a look. So we have this alternating bit, right? That makes sense. This -1 to the k is alternating because we know that the signs are going to go back and forth. The positive negative stuff is going to go back and forth. And then notice we have this 2k plus 1. That's the thing that says only deal with odd exponents. For any value of k, any integer value of k, I should say, if you multiply it by 2 and add 1, you get an odd number. And so again, we use that 2k plus 1 structure in the denominator to get odd factorials as well. So alternating signs, odd exponents, odd factorials, that's our sine function. Now hang on a second. I'm saying odd a lot for this sine function. Let's draw a graph of the sine function really quick, just to make sure we know what's going on. All that kind of stuff. Oh boy, that's a terrible sine function. Let me fix that. Let's draw it again. Here we go. Better. Don't we remember something about this function being odd symmetric? It's got this nice rotational symmetry around the origin. That is not an accident that we have odd exponents only and we have odd symmetry in this function. Interesting. All right, so anyways, we've got that series. What's the interval of convergence? That's a question we might want to ask. And then also the question is, do we know that on its interval of convergence, this series actually does converge to the sine function? Hopefully, right? If not, then this Taylor series is kind of useless. We want to actually build a series that converges to the function we think it does. So let's first just talk about convergence in general. And this shouldn't be too bad. We're good at testing series at this point. We can see there's this nice factorial in the bottom. We're going to throw a good old-fashioned ratio test on here. Now, remember the ratio test uses a limit of the k plus first term over the kth term, but it only is allowed to deal with positive stuff. So that means we have to apply absolute values to everything. Now, the alternating part, this -1 to the k, if we throw absolute values on that, it just becomes 1. Because those terms are either -1 or +1, and so the absolute value is 1 in either case. But x could so far be, I don't know what, any value. So let's throw some absolute values on that to make sure that there aren't any negative x's either. All right, so this is what our limit really looks like. We've got the absolute value of x raised to the 2k plus 1, but that's going to be a k plus 1 on the inside where k is. So that's me saying k plus 1 goes right in here. And then I'm going to do the same thing on the bottom with that factorial. I'm going to have a 2 times k plus 1 plus 1. That's my k plus first term. And then I'm going to divide this by the kth term. So that's our regular 2k plus 1 factorial over the absolute value of x to the 2k plus 1. Cool. I can put these absolute values on just x. There we go. Now what I'm going to do is do the distributive property in these exponents and factorials. So notice this is really 2k plus 2 plus 1. So this limit is really the absolute value of x raised to the 2k plus 3 over 2k plus 3 factorial times 2k plus 1 factorial over the absolute value of x raised to the 2k plus 1. Looks awful, but notice, hey, there's a bunch of stuff that's going to cancel, right? Just like we normally see with the ratio test. We have to be a little bit careful, though. We are going to get an x in the numerator and a factorial in the denominator. But notice that there's more than that. Because these exponents and factorials are separated by 2, they're not just going to cancel out directly. Notice, like with the x to the 2k plus 3 over x to the 2k plus 1. If you subtract those exponents, you actually are going to end up with 2 copies of x. So we have x squared, actually. And, oops, this isn't factorial. In the denominator, we're not just left with 2k plus 3, we're also left with 2k plus 1, because these factorials don't start matching up until this one gets a 2k plus 1 in it. So I forget what I said. I think I messed up the wording here, but I'll say it again. So we're going to end up with 2k plus 3 times 2k plus 2, because then our next term down, 2k plus 1, would start canceling out with the numerator. Okay, so once we've got that set up, we can look and see this limit's going to be 0, which is less than 1. So our series converges for all x values. So this is great. Our interval of convergence is negative infinity to infinity. Cool. Make sure you can run through that ratio test. That's going to be super helpful. We got to just be a little careful about the exponents and factorials when you had that k plus 1 index in there. Make sure you distribute the 2 on there. All right, let's talk about what it converges to. You might remember Taylor's remainder theorem from a couple of videos ago. It basically gives a structure for what the remainder, what the error from some polynomial approximation looks like. Take a look at this. You can feel free to pause the video and read over it again if you want. The kind of intuition at the end was that it's the next term, but instead of the derivative, the n plus first derivative, being evaluated at the center, it's evaluated at some point close to the center, or near the center, or between x and the center. That kind of comes from like a mean value thing that we do when we prove it. I don't think we proved it in our video, but that's where that comes from. So for convergence, it should make sense that all we really care about is, does that limit of the remainder go to 0? If the remainder is eventually 0, then as we add an infinite number of terms, our Taylor approximation converges to the actual function. Okay, so for our example, we can go ahead and say our remainder is going to look like this. It's the n plus first derivative evaluated at some unknown point c over n plus 1 factorial times x to the n plus 1. Remember, for our example, our center was 0. Now, our function was the sine function, and that's important because we know the structure of the derivatives. If we look at the limit as n goes to infinity of the absolute value of r sub n, this remainder, what you're going to do is throw an absolute value here and on the rest of it. But the big important thing is that we know that all of these derivatives are either positive or negative, sines or cosines. And then we can get some values that bound the absolute value of the n plus first derivative evaluated at some value c. Because I know that no matter what, sines and cosines at most give us 1. So this is anything between 0 and 1. Normally we'd say between negative 1 and 1, but because we're throwing absolute values on here, everything works out fine. Then you can apply a squeeze theorem and show that this limit does in fact go to 0 pretty easily. I'll let you play with that though. All right, so all this to say, when we build this Taylor series, we found an interval of convergence, and it actually does converge to the sine function. So sine of x is really equal to this infinite series that we had, the alternating odd powers divided by odd factorials. If you take any x value and chuck it into this series, it converges to sine of that value, which is pretty neat. Here's another example for you to take a look at. We want to find the Taylor series centered at 0 for e to the x. I'll let you play with this a little bit, but start finding a bunch of derivatives. That part should be really easy for this function. Then get some coefficient structure, see if you can generalize that, and write out a series for it, just like we did for the sine function. So pause this video, try this for a couple minutes, and then in a second, I'll catch up with you. All right, so let me just write out the function and the derivative. and the second derivative. And I'll probably stop there because it's all going to be the same, right? My coefficient structure then is going to be e to the 0 over 0 factorial. That's just 1. Then on this, we're going to have e to the 0 over 1 factorial times x to the 1. And that's just x. And then we're going to have e to the 0 over 2 factorial times x squared. And that's just x squared over 2 factorial. And you'll notice that this is going to be the same for all of these because every derivative is going to be e to the x. So we don't have any alternations, so there's no negative 1 to the k, but we do have the kth power of x over the kth factorial. Right? The exponent and the factorial in the denominator match. So this is our power series, our Taylor series for e to the x. Now we should check the interval of convergence for this. So we've got this series. You can go ahead and toss a ratio test at it again. And this shouldn't be too bad if you want to pause this and catch up, but I'll just write it out. We're going to look at this limit of the absolute value of x to the k plus 1 over k plus 1 factorial times k factorial over the absolute value of x to the k. Remember, we have to use absolute values because the ratio test forces this to be positive. All right, so then this is really a limit as k goes to infinity of the absolute value of x over k plus 1 after we do all the canceling. And that limit's obviously 0, which is less than 1 for all values of x. And so our interval of convergence is again negative infinity to infinity. So what we're saying is that e to the x is exactly equal to this series for all x values, which is pretty cool. All right, so what we've got now then is that you can, I would encourage you, I'll say, to on your own find the Taylor series centered at 0 for this trig function, cosine of x. And you should notice that it's got some familiar structure because it's going to act a lot like the sine one, not surprisingly. I'll let you do that on your own. There are plenty of examples of people doing this around, so if you want to look stuff up there, you can do it. I'm not going to try and recreate the wheel here, but I do want to show you this one. Go ahead and find the Taylor series centered at 0 for this function, e to the 2x. Now, you could do this in a couple of different ways. The first way that you could think about this is you could say, all right, let's find derivatives. I know I can do this. We're going to use chain rule over and over and over again. I'm going to keep getting these extra multiples of 2 floating around out front every time I differentiate this thing. No problem. That's just going to give me powers of 2. I can figure that structure out. Or if you want, what you can do is say, well, wait a second. I already know this one. I'm going to count this as like a known series from here on out. Let's just pretend that we've got this locked in our memory, even if you don't yet. And eventually you will. And I can notice that this is just 2x composed inside of e to the x. And so shouldn't it be 2x composed inside of the Taylor series for that? Oh, this is just like the examples that we were doing earlier with that geometric series. And so shouldn't e to the 2x really just be the series from k equals 0 to infinity of 2 to the k, x to the k, over k factorial? And the interval of convergence, it's going to be when 2x is in our original interval of convergence. And that's pretty easy. Our new interval of convergence is just going to be negative infinity to infinity. So we can use those properties of power series to construct Taylor series without having to go through all the differentiation. Now in this example, it wouldn't actually have been that bad to just write out some derivatives and see what's going on with it. That's not that hard. But as we get to harder and harder examples of things, It might be more and more annoying to do that. One last one that I'll leave you with. I didn't plan for us to do this one, but I do want to show it because it is kind of fun, is to do this example. Let's do x squared sine of, well, let's just do x sine of x squared. How about that? Hopefully you can see already that this is going to be a bear to try and do by hand, to write out all the derivatives, because you're going to have to do product and chain rule. But remember, you already have this Taylor series locked and loaded and ready to go. Sine of x is just the alternating odd power, odd factorial series. And we know then that sine of x squared is just x squared inside sine of x. And so it's x squared inside of that series with the alternating odd powers and odd factorials. And so we can say sine of x squared is going to equal, still alternating, but now we have x squared raised to the 2k plus 1 over 2k plus 1 factorial. So hang with me. We still have this alternating. We still have a 2k plus 1 factorial. But now we have x raised to the 4k plus 2. Then, if we want to find x times sine of x squared, isn't that just x times this series? Oh, it's a lot to write out every time, isn't it? And can't we multiply that little tiny power function inside this series and get, x to the 4k plus 3 over 2k plus 1 factorial? And we're done. So we can just use those properties to build Taylor series from other known Taylor series. So it's going to be really important for us to get a couple of these ready to go. Get the exponential function, the sine function, and the cosine function as well locked and loaded in your memory. So go ahead, mess around with those 3 examples enough times where you can see all the connections. We also have one for our inverse tangent function. In our last example, or our last video, we ended with that one. And we'll see a couple more as we go, where we'll be able to build these things up pretty nicely, get some Taylor series representations of functions that we can then use to connect to other things. So we'll do a lot with this, but this is a pretty good way where we can connect all this stuff together, and we'll stop it right here.